Thanks, Insin. Hi, everyone. For those of you who don't know me, I'm an ex-signaling engineer, so to come and speak in front of the PWI is I think, brave or stupid. Just on the signal engineer point, I really enjoyed Sinsin's presentation, and it was quite interesting because traditionally we've blamed points failures to voiding. We've now got something else to blame in the discontinuity of the rail, so quite interesting. So I said I've been looking at points for 10 years, and an opportunity came up, to somebody to look at cast crossings, and my name was put forward, and I've been doing it now for 18 months, and I thought, really, cast crossings is just a lump of metal? But boy, was I wrong, because these are live issues that have happened in the last 18 to 24 months, and that's quite a powerful slide, I think, because it really homes in on what the issues are and how costly they can be to the business and present safety risks. So I shared this slide with the ORR last Friday because they're obviously interested in cast crossing failures. So the pressure's really on us at the moment. So it's great to be able to look to Yann and universities to help us with some of the research. Two photographs on there I want to home in on is early indication warnings. So the top row, second one in, you can just see this faint crack starting to appear, but all the two crossings to the right of it are preceding those kind of cracks. They are the same designer crossing. And then on the bottom left, again, that's an early warning indication of a crack, and the photograph to the immediate right is sort of the same issue. So some powerful stuff there. So, scale of the task. People are saying, how are you going to measure success of cast crossings? What's been done in the past? And I'm only going to go back to 2006. There'll be probably people in the room that can go back a long further. But for me, 2006 is when we got the NR60 nose and wing profile. I won't read these out, but you can see EDH came in at 2013. Thirsk is an important one for me. I wasn't in the team at the time, but it's the flagship NR60 Mark II crossing. And that's installed at Thirsk, so we're going back there in a couple of weeks to see how it's performing, and so far, so good. I don't want to jinx it, but yeah. For me then, I mentioned I was in front of the ORR, and before they came into the room, I wrote a list of things I've been working on in the past 18 months, and I wrote 10 things down. Issues that are going on at Waterloo, we've had a couple of issues down at Stoats Nest, and those 10 things, I looked back and I thought, there's 8 things on there which are reactive. We're not as good as we could be doing proactive stuff. So I want to focus on the proactive stuff at the moment, which leads me on to the new specification. It's taken over a year to write, and it's really challenged me technically. But it's published, and I'm briefing the standards brief in Network Rail tomorrow. So take a sigh of relief because it's finally out there. There's people in the room who have had a good input into that. Jeff and I can see Dave, Pete there have all helped greatly with that. So thanks, guys. We're there. So next on to the line, so future stuff moving on. NR60 Mark II crossing is going to become business as usual. There's a lot of orders coming in now for NR60 Mark II, so it's great that they will have an asset that's been optimized. Next up is we've got to do the same for NR56 and obtuse. And then going back to Ian Coleman, Phil Winship's area, what are we going to do? We're going to look at additive manufacturing, new materials. So what have we done with cast manganese for years? Have we challenged new materials? Have they been a success? Have they been a failure? Building on from what Phil mentioned, how cool would it be, if I was a section manager now and I got my phone and I get an SMS to say, text message, that cast crossing has just received a dynamic impact higher than above it ever seen before. Let's go out and have a look. That's the kind of, we need to keep it real, and that's where we need to move towards. And I put swing nose crossings on there. There's a big debate about those, but let's be real. If we can reduce the dynamic impact, we're going to reduce failures. So touching on the specification I talked about, why I think it was such a big challenge was because it hasn't been looked at for years. I think, 2002 was the last time it was published. it has in there a lot of European standards referred to and Network Rail standards. So it's pushed me, you know, radiography, welding. It's a bit of a complex document. It also has a number of European documents that have been written since 2002. So tying in the good things in those documents has been a challenge. But the key thing is the new processes that I'm trying to introduce. Product acceptance. We've filled in some product acceptance applications in the last few weeks for new crossing designs, so that's exciting. DFR, design for reliability, that's a new theme, relatively new theme in Network Rail. Common safety methods for risk, that's also in there, and FEA. And Yann will cover in a bit more detail later on, multi-body simulation. This slide for me is the key change that I think we've introduced, and Yann will cover this in a bit more detail, and I've seen Yann's slides, he's got a far better one than this, so I won't dwell on it too much. But the table is the important thing for me. I think in Europe, they run a similar wheel set, whereas in the UK, we've got P5 new and old, P8 new and worn, P10 worn, and P10 hollow. And across the right are the dimensions that we look at. So quite a lot going on there in the UK industry, so it'd be lovely to say, right, let's have one wheel design going forward and let's keep it to a good state of wear. Continuous improvements. So what the specification is also trying to do is to say, right, let's take a step back. We know our crossings are failing. Let's do some analysis to find out why. So stress analysis is something we're keen to push out and see if we can do some research and understand where the high stress concentration areas are and what things can we introduce to minimize the impact and make the asset stronger. So this isn't just for me a kind of a crossings issue. I had a video sent to me on Monday of a set of points going into Paddington, and the video basically said, why are these points failing? I mean, from a video, how are you going to tell? But it's the same. I just get photographs of crossings with cracks or breaks in them saying, can you tell us what went on here? And I've been working with the suppliers, and in fairness, when I go to them with a crossing issue, the first thing they ask is, can we have some more data, please? So one of the things I've introduced is these forms, crossing defect form. They've been successful partly. I've had about 25 come back to me in the last 3 or 4 months since they've been introduced. But you can just see there are some signs in these forms that give us an indication rather than just a photograph as to why there are some issues. So I've got to embed this into one of our documents and get it published and make it business as usual. But that's the challenge ahead. I've mentioned we've got lots of different wheel shapes in different states of wear and lots of historic traditional crossing designs. So one of the things, I think it was a paper that Sinsin did a while ago about changing the top intolerance. So we've looked at that with Yann and we've come up with some improvements here. So the dark area are where the impact circle is if we didn't change the top in design. And then if we sort of changed or explored different top-in shapes and different designs, you can see the colored shapes are expanding out. So that's better because we'll have a wider load transfer area. However, that would be great. But I don't know if you've picked up on, the top diagram, the middle, that's the bearer. And what we've done by optimizing the top in performance and getting a wider impact zone, we've now shifted the impact point off the bearer. So ideally, we'd have a larger bearer or a smaller distance between the bearers. But then we think, how are we going to fit those on the modular delivery wagons? And how are we going to do that with the historic ones we've already gone in at 710? So it's great to have some solutions, but we just got to be aware of the constraints and challenge them more. I think this work essentially will drive us to new designs, same as what we've done for Thirsk. We need to do the same perhaps for NR56. So, pulling it back to the work we've done with Huddersfield and the help we've had from Yann and his team, what I mentioned earlier on in the previous diagram, on the left, you can see the different top intolerances we've evaluated. And there you can see the amount of wheel shapes I was talking about with the P5, P10 and P8. So lots of different variables there to consider. And the photograph on the right is, I don't know how well you can see the cutting, but there's some intricate cuts gone on there. It's not just a flat surface or an inclined 1 in 20. There are some clever designs going on there to make the wheel-rail interface as optimized as possible. And on that note, the person that's been doing a lot of the work on our optimization is Yann Bezin.
Thank you, Bleddyn. Good morning, everybody. It's a pleasure to talk to you this morning. So I'll go in a little bit of details about the type of work we've done here. But first of all, I'll just give a brief introduction. Huddersfield University has been mentioned quite a few times this morning. We do a wide range of research along the topics on the top there, from traction braking, pantograph, OLE, interaction, safety, and so on. We also a lead for the recent Centre of Excellence in Rolling Stock, which have 3 pilots, one on infrastructure, one on data, led by Birmingham and Southampton, just to note. But what I would concentrate on today is just the part on vehicle and track dynamics that's been introduced this morning, and more specifically the area I'm leading for our institute on switches and crossing research and development. I've worked in this area for a number of years now, and I've engaged with Bleddyn more recently on this project. But we've started working on this topic for quite a while, and there are 3 key aspects we're looking at. We're looking at rail damage and materials, which has been mentioned this morning. We're doing some testing on different range of material. We're looking at wheel rail optimization, and this is the focus of what I'll present afterwards. But we're also doing whole system modeling to look at the support condition, the bearers, how the load spreads onto the turnout. We've done this through a range of funding. So we started from some European projects that some were mentioned this morning, others not, but Capacity for Rail, Into Track. We also have a 5-year grant program, EPSRC, funded by the EPSRC, called Track to the Future, which has funded a lot of the development work here. And then obviously we work closely with Network Rail. Also Progress Rail was mentioned just earlier on. We've had a good working relationship on those topics. So what we're doing basically is looking at the mechanical interaction between vehicle and track in switches. And Sinsin showed a video this morning, so that's a similar type of video. So we're looking at the mechanical properties of the vehicle, the mechanical properties of the track, and we use numerical simulation software, multi-body dynamics, to simulate the behavior of one against the other. And that gives us ideas of forces, acceleration going on within the vehicle, but also onto the track system, onto the wheel and the rail components. So the arrows there are showing you the force vectors applied onto the wheel reacting to going through a switch and then a crossing. So you can see these arrows moving up and down and left and right. So the fundamental principles of a vehicle, a wheel running through a crossing, it looks fairly simplistic viewed from the side or the front, but it's quite a complicated 3D wheel and rail geometry interaction. So it's a bit, it stretches your mind and your head when you think about it. But essentially the wheel is going over the crossing, wheel and rail moves sideways at an angle, the wheel goes down because it's conical, so, and then it's being catch up by the crossing nose stopping, that brings it back up. As you do so, you've got an interaction between the wheel and the track. So this has been studied by Jenkins quite a long time ago, more for rail joints, but it's transferable to the problem of crossing. And there are key parameters driving the forces that we see is the vehicle speed, the dip angle seen by the wheel as it moves up and down, and then the mass and track stiffness, so mass of the wheel and the rail. So you can see there are 2 impacts forces shown on the plots there. The first one, we call the P1, is the first impact of the wheel onto the crossing. So it's very sudden, it lasts in the order of a millisecond, so it's very localized and very high magnitude, but small energy because it's short. However, it coincides with some of the very local damage we see on the nose and the wing. And then you've got a rebound force, that is the wheel set coupled with the cast crossing mass that bounce together onto the track. That lasts a bit longer, of the order of tens of milliseconds. And this is leading to some of the other damage that we've seen about bending, fatigue, cracks, and also ballast migration and ballast settlement below the crossings. Okay, so now if you look, we've looked at the side view. Now looking at the front view, you can see here the crossing wing appearing and then moving away. So you've got the contact on the wing, and then it moves sideways, the wheel drops down, and then it's being captured up by the nose and it moves back up. Okay, so the video is slowed down. That's a vehicle running at 80 kilometers an hour. In reality, that happens very fast. If you've been sitting on the train on the side of the track, you would hear the banging noise. So there's a lot of energy going into that very small movement. So looking at it from another angle, you can see the crossing, and the lines there represents the path of different wheels running over the same crossings. And depending on the shape of the wheel, you would have slightly different contact location. So on the wing rail, we tend to spread the contact in different areas there. You can see a knot one that goes completely on the side there. That's a hollow worn wheel, and I'll mention a bit more about this. So it's a wheel that tends to have a concave shapes because it wears a lot in the center, not on the side. So it's typical of freight vehicle or light rail vehicle as well. Here you've got an idea of the intensity of the force here going on. So we can see the dark spot is our P1 force, and then these yellow dots are the spread of the P2 force afterwards for the different wheels. Now, overlaying again one wheel on the top, we can see P1 and then P2. These are the force vector applied onto the crossing. Okay, so how about going and studying this issue? It's obviously a big system issues. There are plenty of things to consider. We have to consider the speed and the directions of the vehicle, going facing and trailing move on the crossing, through and diverging directions. We have to consider different vehicles with different speeds, permissible speed for each vehicle, different unsprung mass, different suspension system. All this is modeled in these vehicle models there, multi-body dynamic simulations models. And then the payload as well for each vehicle is different. Then we have to look at the crossing shape. So that's where we focus on the NR60 optimization. So we've developed some tools to recreate the 3D shapes of the crossings. We've worked with Progress Rail as well to use their data for the simulations. The angles can vary as well as the shape and the profiling. All these have some incidence on the loads. And then eventually the wheel profile. So far, only a few wheels have been used for assessing the geometry. We've been working with a large sets of wheels. These are giving you an idea of about 800 wheels measured from freight fleets of vehicles. And you can see the spread of shape. We've been using these for the simulation to have a better idea and representation of the variability of load. Other factors that may be influencing what we're doing is coefficient of friction, track irregularity, gauge widening, curvature, signal, and so on. But we tend to ignore these just to keep things simple, because we already have in the order of 1,000 of simulation if you start considering all these factors together. But you have to. Okay, so this is an example of some output coming from the simulation where we can look at the results. On the top, you have the force vector. You can see the P1 and then the rebound P2. And then the middle plot is the position of the wheel vertically. So it comes onto the wing rail, it moves up onto the wing rail because the point of contact shifts onto the side. And then when it goes around here, the wing rail diverges, it starts dropping down, and then it catches contact onto the nose. The black line is a nominal wheel, the blue one is a worn, typically worn wheel. So you can see that we have a slight shift of the first impact loads and slight difference in magnitude of loads. If we look again at the same but with a hollow wheel, then we can see a much bigger difference. The hollow wheel starts climbing up a lot higher because it contacts further field on the wing rail, so it's being brought up further high, yes. And at some point loses the support from the wing rail about here, and it basically drops down, and it's free flying for a while, all this duration there, until it catches the nose around here, and then it moves up the nose, and then we've got a big rebound P2 force as well as a big P1. Okay, so you have a peculiar behavior there that potentially lead to a very different impact on the life of the crossing. So we've done this for many different wheels. Again, we've got black is the nominal one, the blue shades are different worn wheels, and the pink one is our hollow wheel, which is again very different to the others. And we've got 3 different crossing designs. So we looked historically at many different designs. This is a 1056, 1 in 20 wing angle, and this is a horizontal wing called half cant. So you can see very different behavior, very different dip angle shapes. And then this is the Thirsk evaluation against these designs. So you can see something a lot flatter, which leads to much less impact forces on the crossing. So it's a big improvement that is gained by doing things slightly differently. This is showing, it's looking at the same results as before, but it's just peaking the peak force for each of these runs, plotting them on the vertical axis against the position where this impact happens. So this is a 1056 design. The stars are nominal wheels at different speed, and then all the other dots are different worn shapes of wheels. So you can see that if you only consider the nominal one, you're actually missing quite a big part of the equation. So looking at the range and the variability of these loads gives you a better chance to understand life of crossings and the design aspect of it. So we've got facing, direction, and trailing. We've got a very different behavior in facing and trailing. Trailing generally generates high loads. So I'll just flick through some of these. It's basically different design shapes. So that's the 1056. This is the original NR60 Mark II before it was slightly tweaked and redesigned for the Thirsk installation, which is this set of results. So you can see that overall we've managed to reduce most of the impact load from most of the wheels, so I've concentrated them a bit better. So overall there were some improvements to be gained, and they're clearly a lot better than the 1056 crossings. Okay, so that was a work that was done probably 2 years ago now. What we've done at the end of 2018 was to look at the nose topping, and since worked on it quite a few years back as well. So we revisited some of this using this simulation approach, and we looked at a base case scenario. So the same, you've got your peak force there, and then you have the contact point location where this load transition takes place for a base case with many different wheels. We looked at raising the nose up by 0.5 millimeter. So when Sinsin says millimeters matter, they do matter. So if you bring the nose up by half a millimeter, what happens is that you get the majority of these loads are actually going down. So you're picking up the wheel more smoothly before it has time to drop down. So there's a benefit in doing this. On the contrary, if you start bringing your nose down, so that's half a millimeter down, okay, and then 1 millimeter down, and then 2 millimeters down, everything is starting shifting up. So you increase your impact load onto your crossing, and you obviously shorten your life. So that has led to some recommendation for TRK012 on manufacturing tolerances and so on. But it shows that you need to get your initial base design right and get your design as close as possible to what you want to achieve, and then manage your tolerance around this to actually put on track what you intended to do. And this shows so raising the nose by half a mil gives us a reduction of up to 6% in the loads for different crossing, different directions, quite consistently. 2 millimeters down, and you increase your load by up to 14–15%. And probably the life is reduced by that much. Okay, one last technical slide. Sorry, a lot of graphics and dots everywhere. In the current TRK012, there's a strong reference to the Jenkins formula for the P2 force level. So it's just applying this formula. So you take a dip angle value, you factor the speed of the vehicle, track stiffness, and mass. And then you come up with a peak force. So we've done this through the simulation, and we compare the two. This, again, shows all the different topping design for all the different wheels. And these are the forces produced from the multi-body dynamic simulation software. Previously, TRK012 was specifying a 10 millirad applied to Jenkins to give you the force. Based on those sets of results, we only capture about half the forces that we produce and predict from the multi-body dynamic simulation. If you take 20 millirads deep angle, you actually capture most of the forces that we predicted from the simulation. So the new applied value by default is 20 millirad, which should give us a conservative approach. And then the regression line here shows us a systematic 35% over-prediction from the Jenkins formula compared to the multi-body dynamic simulation. So it would be interesting to review this work in the context of crossing, because it was originally done for joints. Okay, so I'll conclude my part of the presentation. So wheel-rail interaction matters. It's a key driver for all the damage that we see, but whether it's fatigue or local rail damage. So it needs to be carefully considered in the design improvement. The range of wheel shape matters. Those variability was mainly from freight vehicle. If it's passenger fleet, they tend to have more consistent shape. They'll turn more often, so it's not a problem. But the freight shapes certainly have a big impact. Although freight wheel seems to be a peculiar case to be considered. The P1 impact force is leading to local damage. It's not really considered or recognized in TRK 012. Maybe it should be more acknowledged. Multi-body simulation, as we've used here, is being introduced in TRK 012 as a way of improving the design, so it's a good thing. P2 formula is slightly over-predicting, so maybe it needs to be investigated further. The complex multi-body dynamic simulation can be replaced by simplified algorithms, so obviously we're going to work towards this so that industry can better take advantage of these calculations. Yeah, and I think that there's still some margin for improvement for future design of an NR60 Mark II, probably using advances manufacturing capabilities as well to design the right shapes the way we want it, and then we'll take some of the lesson learned for the NR56 as further work. And I'll hand it to Bleddyn for the final conclusions.
Yeah, brilliant. Thanks, Yann. I think that's a really good flavour of how important research is to a live issue that we've currently got. So my conclusions, data. I've really struggled to get my head around why we've got lots of dots of spreadsheets in Network Rail, but it's just pulling all that data together and having the time to get some meaningful results. It's something I'm keen to do and deliver, and that's probably my key task going forward, is to get better data and information from it. So I'm working with the crossing defect form, as I showed, but I've also set up now a bi-monthly meeting with route services, because when you buy a new crossing, what I want is information as to why that crossing failed and why do you need a new crossing. So it's just getting it all structured in place. As Yann pointed out, to have the greater intelligence and the opportunity to optimize, I think we now can see the benefits of doing the step back and optimizing through the stress analysis. It's going to give us some good rewards. Conscious of constraints, that's what I'm a bit frustrated with at the moment, because we can see the work that through Yann's simulations, we can come up with a really good top-in and we can come up with really good low forces, but how do we implement that onto the network in live scenarios? So we might have to, well, I think we are, and I'm going to really push this, is try and get a blank sheet and say, right, what does it really need to be going forward? I know we've got issues with traditional and legacy footprint stuff, but we really need to change. I think Ian mentioned earlier on, a step change is needed, I think, if we are going to get the results we need. It's not just us at the centre. The RAM team has been important with this, and that's where the funding needs to come from if we're going to implement these changes. Bit of a controversial one there, but we do need some funding to help us. And to finish off, it's basically more resilient crossings. That's what's needed. Yeah, and more, same as what we've done at Thirsk. So that's it. Cheers, guys.